In our last video, we talked about the Laplace transform and how to calculate the Laplace transform of a function. In this video, we are going to talk about using the Laplace to find solutions to initial value problems. In particular, Laplace transforms are useful for solving initial value problems of linear differential equations with constant coefficients. Here I have the definition of the Laplace transform for your reference for review. And recall, the Laplace transform takes a function, little f of t, and produces a new function, capital F, dependent on the variable s. And the Laplace transform does this by taking our little f, multiplying it by e to the st, and then taking this indefinite integral. Because we want to use the Laplace transforms on differential equations, we need to know what derivatives look like in Laplace transforms. In other words, if we take the nth, we want the Laplace transform of the nth derivative of f. And here is the general formula for this, or here is the formula just for f prime of t. So the Laplace transform of f prime of t is equal to s L of f of t minus f naught. And we can use this repeatedly to find L double prime of t, and then finally f, the nth derivative of t, and the final formula is here. And finally, we will use the Laplace transform to solve initial value problems of linear differential equations with constant coefficients. Our general strategy will, one, to be use the Laplace transform to transform an initial value problem for an unknown function f in the t domain into a simpler algebraic problem for capital F in the s domain. We're going to solve the algebraic problem in f. So again, we've transformed this to a differential equation to an algebraic problem, but then once we find f, we need to find f inverse to get little f. So we're going to invert the transform. And to do that, there is a way to do this in f inverse, invert the transformation, but to do that you need some complex analysis, and just not complex numbers, but you need to know how to integrate complex functions in a complex plane. So we're not going to do that, but we're going to do this by table, and I will show you how to use this table. Last, I want to mention that the most important application of the Laplace transforms are in the study of mechanical vibrations and in the analysis of electric circuits. And I have, for your reference, the review. We went through this, the mechanical vibrations, second-order differential equations, that's not homogeneous, as well as for electric circuits. Now we're going to back up, review the Laplace transform, and look at its derivatives. First, the Laplace transform of f of t, of a function f of t, is equal to the indefinite integral of f of t times e to the minus st, and that will give us a new function called capital F of s. And now we can calculate the Laplace transform of the derivative of f. And the transform of f prime is related to the transform of f. In particular, if f is continuous and f prime is piecewise continuous on an interval from 0 to a, suppose further there exist constants k, a, and m such that the absolute value of f of t is less than or equal to k e to the at for t greater than or equal to m, then the Laplace transform of the derivative of f of t exists for some s greater than a, and moreover we have this formula for the Laplace transform of the derivative of f of t is equal to s times the Laplace transform of f of t minus f naught. And the proof is in the book, and I will not be covering it. I've rewritten the formula for the Laplace of the derivative of f of t here. So it's equal to s times L f of t minus f naught. Again, I just copied this formula here. So from here we can find the derivative, the Laplace transform of the second derivative of f of t. Since the second derivative of f of t is equal to the derivative of f prime of t, the Laplace transform of f double prime of t is equal to s times what this is a derivative of, which is f prime, minus f prime of 0 here. So here again, the relationship, or how you can see this, is this f prime of t. This is when we're looking at f double prime of t, but the relationship between these two is f prime is the derivative of f of t. So in other words, f double prime is the derivative of f prime of t. So here I have f double prime of t is equal to s times, in this case we'll be looking at what f of t is a derivative of, which is f prime of t minus f prime of 0. And now substituting for f prime of t over here with what we have in the previous line, we get s times our L of f prime of t, which is s, L of f of t minus f naught, minus our f prime of 0. So multiplying everything out, I get s squared L of f of t minus s f naught minus f prime of 0, which I have written that formula over here. Similarly, I can calculate the Laplace transform of the triple derivative of f of t. So that's going to be s L of f double prime of t minus f double prime of 0. And now I can plug in my L of f double prime of t from my previous line. So I get my s, my f double prime of t, L of f double prime of t minus f double prime. So what you see is here I have to multiply this f double prime, everything gets multiplied by s squared. So I have s cubed now, L of f of t minus s squared f naught minus s f prime of 0 plus minus f double prime. So the pattern is every time you take a derivative, you're going to multiply everything in the previous line by s and then add another f of n minus 1 prime of 0. And this is the general formula here. So I wouldn't necessarily memorize each of these formulas, but I would memorize the starting formula, and I might memorize this pattern here. Those are the two things. All the stuff in between I would just derive from one of these two forms. Now that we know how to take the Laplace of the derivative, we can use Laplace to solve initial value problems. And I'm also going to remind you that the Laplace transform is a linear transformation, and we will be using that fact. Our first example is to use the Laplace transform to solve the initial value problem of the linear differential equation with constant coefficients y double prime minus y prime minus 2y equals 0, satisfying the initial conditions y of 0 equals 1, y prime of 0 is equal to 0. And I have these two Laplace transforms that we had calculated in our previous video. So the Laplace transform of 1 we had calculated in our previous video as 1 over s. And the Laplace transform of e to the at is equal to 1 over s minus a. And for a quick review, here I have the formula for the Laplace transform. So the Laplace transform of 1 is equal to capital F of s, which is the indefinite integral e to the minus st times our f of t. In this case, we have 1. So here's the indefinite integral. You can take a look at it, and we end up with 1 over s for s greater than 0. For e to the at, our Laplace transform is the indefinite integral of e to the minus st times our f of t, which is e to the at. So you can look at the indefinite integral, and we get 1 over s minus a. So here we are with our differential equation, as well as our two Laplace transforms for your reference. And a quick review on how we would do this without the Laplace transform. We would look at the characteristic equation, which is just the coefficients in front of our y double prime, y prime, and y terms. So we have our coefficient is 1, r squared, minus 1 is our coefficient in front of r, and then minus 2y. And that will give us our polynomial, r minus 2, r plus 1 equals 0. So r is equal to 2 and minus 1. So these will be our exponents for e to the 2t and e to the minus 1t. And both of these are multiplied by constant coefficient c1 and c2. We calculate y prime of t, that would give us 2c1 e to the 2t minus c2 e to the t, and we use our boundary condition setting that equal to 0. That tells us that 2c1 minus c2 equals 0. Also, this boundary initial value condition, plugging in 0 here, tells us that c1 plus c2 is equal to 1. And finally, these two conditions together tell us that C1 is equal to 1/3 and C2 is equal to 2/3. With the Laplace transform, and honestly, this is such an easy equation, we're not going to get a lot of benefit by doing this by the Laplace transform, but it's a good one for us to start as an example. So with the Laplace transform, we can look at what is the Laplace transform of y double prime minus y prime minus 2y. And because of the Laplace is linear, first we can separate this out by each term. So we have Ly double prime minus Ly prime minus, and it'd be L2y, but then we can also take out the constant coefficient, so we have minus 2L of y. Now we can use our formulas for derivatives. Since y double prime is the derivative of y prime, this is SL of y prime minus y prime 0. Here, for y prime, we get SL of y minus y of 0, and we have minus 2Ly. We can then simplify this, or take our derivative. This part, our L of y prime, is equal to SL of y minus y of 0. Then we still need to multiply by s, and we have our y prime of 0. This stays the same. This gets carried down as well. So now we have our s squared L of y minus, here we have our s times y naught, this s times this y naught, minus y prime of 0 minus s L of y plus y naught minus 2Ly. Another way, you could have gone directly from here to here, noticing the pattern. So if this is the nth derivative, that means we're going to take s to the n, that's s squared, L of y, minus, and then we just keep subtracting s, 1 from our s. So here we have s squared, so we go to s, y of 0, minus, and then we take off 1 from the power here, which gives us 1, minus y prime of 0. Similarly, we can go to the y term, and we have, where is the y term? We're looking at y prime. So since this is the first derivative, we're going to have s to the 1 times L of y plus y0. So this is pretty quick to do through all these steps, but knowing how to use this formula will come in more handy when you have like f to the 4th or 5th. Continuing now from this line, I'm going to let y of s equal L of y, and I'm going to group my y of s, or my L of y terms. So I have my s squared, I have my minus s, and I have my minus 2. I'm going to group my y0 terms, so I have 1 here, minus s here, and then I have my y prime equals 0. Now I can use my initial conditions just to kind of get rid of these y0. So my y0s is equal to 1, and my y prime is equal to 0. And now I can solve algebraically for y of s is equal to s minus 1 over s minus 2 s plus 1. And remember, our y of s is equal to the Laplace transform of the solution y we are looking for. And I have rewritten that here. So we have our Laplace transform, and that's equal to y of s, which is equal to s minus 1 over s minus 2 s plus 1. So this is great if we wanted to know what the Laplace transform is, but what we wanted to find was y. We wanted to find the y of t, whose Laplace transform is s minus 1 over s minus 2 s plus 1. I haven't told you how to take the inverse, but what we are going to do is start by using partial fractions. So we have s minus 1, s minus 2, s plus 1, and we want to break this fraction apart into a over s minus 2 plus b over s minus 1, because we had, and the reason why we want to do this is we know what the Laplace transform is of something of 1 over s minus a. We know that 1 over s minus a is the Laplace transform of e to the at. So we kind of want this simplified form so we can get something we know. Anyway, so here, to use partial fractions, we have this equation here, so we can multiply both sides of our equation by s minus 2 s plus 1. So over here, we're just going to get s minus 1 on top, and which is here. And then when we multiply this part of the fraction, a over s minus 2 by s minus 2 s plus 1, the s minus 2's cancel out, and we get a times s plus 1, We multiply b over s plus 1 by s minus 2s plus 1. The s plus 1's cancel out, and we get b times s minus 2. And then we solve algebraically, and we get b equals 2/3 and a equals 1/3. So y of s is equal to 1/3 over s minus 2 plus 2/3 s plus 1. So because Laplace is linear, that means that's 1/3 the Laplace transform, looking at this equation here, e to the 2t plus 2/3 the Laplace transform of e to the minus t. Because the Laplace transform of e to the 2t, right, is equal to, here a would be equal to 2, 1 over s minus 2, which is exactly this here. So we're kind of just using this formula backwards. So this is our final answer. Our y of t is equal to 1/3 e to the 2t plus 2/3 e to the minus t, because this is the function whose Laplace transform is equal to 1/3 over s minus 2 plus 2/3 s plus 1. At this point, it was probably easier just to use the characteristic equation to solve this problem, but this method does become more convenient, especially when you have a non-homogeneous differential equation. And so we're going to see an example of that in a minute. And I'm going to tell you one of the reasons why this is Laplace is particularly good if this is not a homogeneous equation is because remember when we had a second order differential equation that was non-homogeneous, the first step was to solve the homogeneous differential equation. Okay, that was fine. But then for the non-homogeneous, the next thing we had to do was the method of undetermined coefficients. And if you recall, that was sort of involved. So we're going to have a big win when this is non-homogeneous. And the next thing we're going to do is to solve the second order differential equations with constant coefficients. And we're going to solve in general for constant coefficients a, b, and c, but we're going to solve the non-homogeneous equation. And naturally, the first step, if we're going to use Laplace, is we're going to look at the Laplace transform of a, y double prime plus b, y prime plus c, y. And because it's linear, we're going to break that up into a times l, y double prime plus b, l, y prime plus c, l of y. You can follow through this algebra here, or you can go straight to this formula here, and I'm going to get a s squared l of y minus a s y naught minus a y prime of 0. That's for this a y double prime. And for my b y prime, I'm going to get b s l y minus b y naught. And then for my c of l y, I'm just going to have c of l y. Like I did in our last example, I'm going to let y of s equal to our Laplace transform of y. And also, I'm going to let f of s now equal to the Laplace transform of our f of t, what is over here making our equation non-homogeneous. Before, this was a homogeneous equation, so this was just equal to 0. F of s was equal to 0. In this case, it's going to be equal to something, which we'll denote as f of s. And like we did in our last example, we're going to group all of our y-s's together. So I have an a-s squared, I have a b-s, and I have a c. We're going to group, and I'm going to move it to the other side of the equation for now. I'm going to have my a-s y naught, and again, since I move it to the other side of the equation, it becomes positive. And I have my b y naught. Oh, and I also have my a y prime of 0. And I think that takes care of all of our terms here. So I can solve this, and I get ys is equal to as plus b y naught plus a y prime of 0, as squared plus bs plus c, plus, now I also need my f of s over as squared plus bs plus c. And here's what our solution is going to look like. And when we actually have a problem with a and b's and c's defined, we're going to use our partial fractions to be able to decompose this part here. And the advantages now of Laplace of this equation, and we will do an example with actual a, b, and c's, but the advantages first is the transform ys of the unknown function y of t is found by solving an algebraic equation. Granted, you do have to do partial fractions, but it is algebraic. rather than a differential equation. And this is the key to understanding the usefulness of the Laplace transform for solving linear, constant coefficient, ordinary differential equations, and ordinary as opposed to partial differential equations. The solution satisfying the given initial conditions is automatically found, so that the task of determining appropriate values for the arbitrary constants in the general solution does not arise. In other words, we've already incorporated this y naught and y prime, so we don't have to then go back and solve for the constants. Furthermore, non-homogeneous equations are handled exactly the same way as homogeneous. It is not necessary to solve the corresponding homogeneous equation first. So in our example, you will see how all of these things, these extra steps you had to do before Laplace, just kind of go away. So this method can be applied in the same way to higher order equations as long as we assume that the solution satisfies the condition that f prime up to fn minus 1 are continuous and fn is piecewise continuous, and there exist constants k, m, and a such that the absolute value of f of t is less than k e to the at for t greater than or equal to m. And there is another note. So I've been talking about how you can find this ys, the Laplace transform, but like our example that we had before, once we found the Laplace transform, we looked up to see what function gave us that Laplace transform. In other words, what we needed was an inverse Laplace, which is the main difficulty that occurs in solving initial value problems by Laplace. It lies in the problem of determining the function y at t corresponding to the transform. This problem is known as the inverse problem for the Laplace transform, and y of t is called the inverse Laplace transform corresponding to y of s. And the process of finding y of t is known as inverting the Laplace transform. And we can use this notation, Laplace transform inverse of y of s, to denote that's how we're going to find y. And there is a general formula for the inverse Laplace transform, but it requires a familiarity with the functions of complex variables, and we are not going to cover that. And by familiarity with complex variables, I mean you'd have to know how to integrate a complex function in the complex plane. And so what we will use instead is a table, which I showed you in the initial overview slide, and you'll see it again. One last note, it can be shown that if f and g are continuous functions with the same Laplace transform, then f and g must be identical. On the other hand, if f and g are only piecewise continuous, they may differ at one or more points of discontinuity, and you have the same Laplace transform. This lack of uniqueness of the inverse Laplace transform for piecewise continuous functions is of no practical significance in applications. Thus, there is essentially a one-to-one correspondence between functions and their Laplace transform. So when you use that inverse, you know that you're getting the correct function. Here's the table in your book that we will be using to find inverse Laplace transforms, and all differential equations books has this type of table, or you can look one up on the internet. But you can also screenshot this so you can use it. I'll have it off to the side for reference, but it's kind of a little bit small. And the way we are going to approach these problems is one, we're going to use the Laplace transform to transform an initial value problem for an unknown function f in the t domain into a simpler algebraic problem for capital F in the s domain. So we'll use the Laplace transform. We're going to solve the algebraic problem for capital F, and then we're going to invert the transform to get back little f. And again, we're not going to cover the formula to go from capital F to little f because that involves complex analysis, but we are going to use the table that I just showed you. Here's the table, and the first example is to find the solution of the equation y double prime plus y equals sine of 2t, where y of 0 is equal to 2 and y prime of 0 is equal to 1. We're going to start by taking the Laplace transform of y double prime plus y, which is equal to, because it's linear, L of y double prime plus L of y. Looking up our table, we have s squared ly minus s y naught minus y prime of 0 plus L of y. And that's equal to the Laplace transform of what's on the right, sine of 2t. So here, if we let y of s equal to the Laplace transform of y, we have s squared y of s minus s y naught minus y prime of 0 plus y of s is equal to, and I just looked up on the table, the Laplace transform of sine of 2t is equal to, in this case, a is equal to 2, so it's 2 over s squared plus 4. I'm going to group my ys terms together, so I have an s squared and I have a 1, and then I'm going to move my other terms, my sy0 and my minus y naught, to the other side over here with this 2 over s squared plus 4. And then I can plug in my initial conditions. My y of 0 is equal to 2, so I have my 2s, and my y prime of 0 is equal to 1, so then I have my 1 over here. So now if I divide both sides of this equation by s squared plus 1, I get y of s is equal to 1 over s squared plus 1, 2 times s squared plus 4 plus 2s plus 1. So I've moved that equation for y of s up here to give myself more room. Algebraically, you can see that's equal to 2s cubed plus s squared plus 8s plus 6 over s squared plus 1, s squared plus 4. Now using partial fractions, because I want to break this down into something that looks like maybe a over s squared plus a squared. So I'm going to have my as plus b over s squared plus 1, the first part of my fraction over here, of my denominator, plus cs plus d over s squared plus 4, the second part of my denominator. You can follow this algebra, and you'll see that a is going to be equal to 2, b is equal to 5/3, c is equal to 0, and d is equal to negative 2/3. So I've moved that, I've plugged in for a, I plugged in 2, for b I've plugged in my 5/3, for c I have 0, and d is equal to minus 2/3, and again it's equal to this equation over here, which is L of sine of 2t. And now I can use my table over here. I'm going to set ys equal to this sum over here, and then pulling out some of the constants, I get 2s over s squared plus 1 plus 5/3 1 over s squared plus 1 minus 2/3 1 over s squared plus 4. And I've just moved that up over here for our reference, and so I could have more space. So now I'm going to look at our table for something that looks like s over s squared plus 1. So when I look down here for something like s over s squared plus a, I see that the cosine function fits the bill. So this then, for my y of t, I have 2 times cosine of t. When I take the Laplace, I'm going to get 2 times s over s squared plus 1. So that's what I have for this part. Now I need to look for something that looks like s squared plus 1. Actually, that's the same thing. I could have, is that right? Let me look. No, not an s, just an a over s squared plus 1. So this works when a is equal to 1, and that's my sine function here. When a is equal to 1, so I'm going to have my 5/3 sine of 1t. And last, again, I have my 1 over s squared plus 4, so that's still my sine of at, except now because I have s squared plus 4, a must equal to 2. So this means here, this is going to be 1/3 sine of 2t, because the Laplace transform of sine of 2t, let me underline this, is going to give me, sine of 2t would give me my 2 over here, s squared plus 4. And this is it. This here is my solution. So you can see, if we compare this, and we're not going to do this, but if we had done this without Laplace, first we would have had to solve the homogeneous equation. Then we would have had to solve we would have found the particular solution to the non-homogeneous equation using the method of undetermined coefficients. And then we would have used our initial conditions to find the value of the coefficients C1 and C2. Whereas here, it just kind of, we avoided like having to use these initial conditions. I mean, we kind of put them in, but it happened very easily. We didn't have to solve the non-homogeneous and the homogeneous. It all kind of fell out fairly quickly. And the only problem is we had to use a table for the inverse Laplace transforms because I am assuming that you may not have had complex analysis yet. And if you have had complex analysis, then you can use your complex analysis to solve this. My next example is to find the solution of y, the fourth derivative of y minus y equals 0, where y not equals 0 and y prime of 0 is equal to 1, y double prime is equal to 0 is equal to 0, and y triple prime of 0 is equal to 0. And this is where, when we tried to find the equation for L of y to the fourth minus y, that this formula comes in handy. So we have s to the n, here the fourth derivative, so it's s to the fourth L of y minus, and then we subtract 1 from s, so we have s3 f naught minus, subtract 1, s2, and then f prime, minus, subtracting 1 we get s f double prime, subtracting 1 we get 1 times f triple prime, and then finally we have our L of y from this minus y here. We are going to let y of s equal L of y, so we have our s to the fourth y of s minus s cubed y naught minus s squared y prime of 0 minus s y double prime minus y triple prime minus ys, and then we're going to plug in our initial conditions, and we get s to the fourth. Here we have y0 is equal to 0. We have our s squared y prime of 0 is equal to 1, so we have s squared times 1. And our y double prime at 0 is equal to 0, so that's 0. And our y triple prime is 0 is 0. And then we have our minus ys. So when we solve for ys, we get s squared over s to the fourth minus 1. And I've rewritten that here. Our y of s is s squared, s to the fourth minus 1. Looking over here, we don't have anything s to the fourth. So, sort of here, but we don't have the n factorial. So we're going to have to use our partial fractions. So s to the fourth, we're looking for something that looks like s squared plus 1 and s squared minus 1, and as plus b on top and cs plus d on top over here. So you can follow through the algebra, and I get that a and c are equal to 0, and b and d are equal to 1/2. So in other words, my ys is 1/2 1 over s squared plus 1 plus 1/2 1 over s squared minus 1. And looking this up on our table, so we have our 1/2 and s squared plus 1, that's our cosine again, where a is equal to 1. So we have cosine of t, and our s squared minus 1, s squared minus 1 over here. That's our sinh, where sinh of at, where a is equal to, here we have, is equal to 1. So we have 1/2 sinh of t. And this is our solution. In this video, we talked about Laplace transforms and how to use them to solve solutions of initial value problems. We started with a quick review of the Laplace transform and the definition of the Laplace transform in terms of this indefinite integral here. And we also noted that the Laplace transform is a linear transformation, which became very useful to us. Then we talked about the Laplace transform of the derivative of a function. So the Laplace transform of f prime of t is equal to s L of f of t minus f of 0. And then we saw that we have this formula for f double prime of t, and basically the formula for the nth derivative of f equals this pattern, this formula here. So we have this table because we were using this to solve initial value problems, and the approach we had was first to take the Laplace transform of an initial value problem for an unknown function f in the t domain into a simpler algebraic problem for capital F in the s domain. Then we solved the problem for capital F, often using partial fractions. Then to go from capital F back to f, we need an inverse transform. But rather than calculating the inverse transform, which would involve complex analysis, we used this table here. And one last note is that the most important applications of the Laplace transform are in the study of mechanical vibrations, given by this second-order differential equation that's not homogeneous, and also in the analysis of electrical circuits with this differential equation. And the Laplace transform gives us several big wins, and that it's much easier to do, especially when you have a non-homogeneous equation. So that's it for this video. Thank you for watching.